Hi, everyone, and welcome to today's session. This is part two from the practical lab experiments in oil and gas industry. You've been requesting this part two. So due to the technical issues that we had in part one, we decided to record this one so the voice is smooth and that you guys can benefit the maximum. So without any further ado, let me introduce our speaker for the day. Our speaker is, of course, the infamous Dr. Rehab El-Maghraby. Dr. Rehab is currently an associate professor of chemical engineering and petroleum refinery at Faculty of Petroleum and Mining at Swayze University. She holds a PhD degree in petroleum engineering from Imperial College of London in UK 2013. Dr. Rehab is among the first Egyptian women to receive a PhD in petroleum engineering. She holds a master's and bachelor's degree from Suez Canal University. She is the PI of the Enhanced Oil Recovery Lab at Swayze University. She published her research work in many international journals and conferences, and she's currently supervising many master's and PhD students on research topics such as enhanced oil recovery, CO2 capture, and separation and corrosion inhibition. Dr. Heb, the floor is yours.
Yeah, okay. Thank you, Mihal. Shukran. So now it is part two for practical lab experiment on oil and gas, and this is what we have. If you didn't watch part one, I would recommend you to start first by watching part one, so you can catch all the expression that I will going to tell in this lecture. So for this lecture, we are going to talk about capillary pressure, mercury injection capillary pressure and pore size distribution, and the enhanced oil recovery experiment. If we have time, we will go through the CO2 storage and micro CT experiments. So let's start first with the capillary pressure definition and experiment. So why capillary pressure in general is important? Why we want to measure the capillary pressure in our lab? So in general, capillary pressure is important. It will give you an indication of the vertical distribution of fluid such as oil, water, and gas in your reservoir. Because in your reservoir, according to the height, the saturation is changing as you go to the top. So more oil you can find to the top at the top of your reservoir. So this is captured by the capillary pressure saturation curve. Also, it can give you an estimate of the hydrocarbon reserve by knowing the initial oil residue, and also after water flooding, you can get the residual oil saturation. So capillary pressure in general, it is a pressure difference between the non-wetting phase. So the pressure of the non-wetting phase take away the pressure of the wetting phase. So according to this equation, so the capillary pressure is the pressure of the non-wetting phase, take away the pressure of the wetting phase. Okay, it is a pressure difference. So let's start from the very beginning. If you have a beaker containing water in this beaker, so you have water, and on top of this water there is oil. Because there is a difference in density, you will find the oil floating on the top of the water, and there is a nice line separating this oil and water contact. If you place a capillary tube in this water, what will happen that the water start to rise in this capillary tube. This will, and it will not rise forever. It will stop at a certain height. This height represents the equilibrium between the gravitational force and the capillary force. Okay, so this height is judged by or governed by the capillary force and the gravitational force. So if we want to express the capillary force, it can be as shown here in this equation. So the capillary force is the relation relating interfacial tension between oil and the brine. If we have oil and water, the contact angle between oil and water and also it is the property of the rock or the capillary tube material. And the radius here is, if you are talking about the rock, so it is the radius of the throat of the rock. If you are talking about the capillary tube, so it is the radius of this capillary tube. So according to this, this is how you can calculate your capillary pressure. So because I told you there is this height, the height of where the water will rise in this capillary tube is governed by the equilibrium of capillary force, which is acting upward, and the gravitational force, which is acting downward. So this can be expressed with this equation. Okay. So if we just place this, the value of the capillary pressure in this, substitute by this value here, so you can get an expression for height. So the height is a relation of interfacial tension, contact angle, the gravity, and the difference, the density difference between the oil and the water or brine, and the radius of the capillary rise. So this equation represents the height or the capillary rise of the water onto in this capillary tube, or in if we take this capillary tube as a pool, so it is the height of the water in this, or as a reservoir, it is the height of your water in this reservoir. So how can we, so as you can see, there is a relation between the height and the radius. So the height and radius, there is they are not inversely proportional. So you can see that if the radius of your capillary tube is large, you will find that the height will be small. The amount, so the water will rise a very, very small amount. Okay, but if the radius is very small, you will find that the height of the water will be high. So imagine here we have some bundle of capillary tubes with different radius, and you will find that the height of water in this tube is varying. This variation is due to this expression, the relation between the height and the radius, because everything is the same actually, because the interfacial tension is constant, the contact angle is constant, gravity and the density is the same also for all the water and for water and oil. But the difference here is the radius of the capillary tube. So what you will find that the water will rise at a different height. So at level A, okay, if we draw a line through this level, what you can find here is that at this level, all are water, 100% saturation of water. At this level, water here and water here, or 100% saturation of water. Okay. So what about level B? If we draw a line through this level B, you will find that there is some, so like there is a saturation, is not all oil or water. So this is a combination between water and oil with a different, because of the variation of the height, caused us to have a variation of saturation in this capillary tube. I want you to catch this is as what will happen in your reservoir. So what about level C? So as you go further in the height, or increase further in your height, so if you draw a line here, you will find 100% saturation of oil. Actually, you cannot in your reservoir have 100% saturation of oil, because there is minimum amount of water, whatever the pressure or whatever the action you are taking, or for trying to force this water to go outside of this port, you will not let it. You cannot get rid of all the water in your pores. You have to reach irreducible water saturation, or what we are calling connate water saturation. So imagine what I told you here on a reservoir. So actually, in our reservoir during oil migration, so oil start to migrate. So the case I'm telling you here. So our reservoir is 100% saturated with water, and oil started to migrate. After migration and having equilibrium between the gravitational force and the capillary force in our reservoir, we will find a high distribution of the saturation, vertical distribution according to the height. So starting with 100% saturation of water, to the top we will go, and the amount of oil will increase until we reach the maximum amount of oil that you will find in your reservoir. So all this can be expressed and identified of this height using capillary pressure, and I will show you how we can use the capillary pressure to calculate this height. So we have actually 3 zones in our reservoir, 3 main zones. The water zone, which we only have water, only 100% saturation with water. So from the start here, so the free water level here, and then all this zone is 100% saturated with water. The first oil was able to invade this pore will happen at the this pressure is called the threshold pressure. Okay, so at this level, so the water will be 100% from the free water level up to the threshold pressure, which is equivalent to the oil, which is represented by the oil water contact. So it is as the oil water contact, it is the first drop of oil or the first part of oil that you can find, and it will be the lowest saturation of oil in your reservoir. So the second zone here is the transition zone. So in this transition zone, actually we'll find the oil saturation is increasing from this point up to the highest at the end. So from the threshold pressure, which is the minimum pressure required for the oil to invade the pore, and I will also discuss this later. So for this, so we will start with oil contact, so the smallest saturation of oil, and we will go to the top. The higher we go, the higher the saturation of oil that we find, until we reach something called connate water saturation or irreducible water saturation, which is amount of water, the minimum amount of water. You cannot get rid of the rest of the water in your reservoir. So this will be the end of the transition zone. So there will be a variation or a changing in the saturation in this zone. The last zone is the oil-based zone. So as you go outside, once you reach connate water saturation, you cannot reach a higher oil saturation. At this stage, it is the initial oil saturation. So once you open your reservoir, this is the amount, the maximum amount of oil you will find in this pore. So along this zone, this is a constant oil saturation, no change in the. I am proposing this is a static condition, okay, no production. So you will find there is no change in the oil saturation and no change in the water saturation, because the water saturation reaches its minimum. You cannot go lower than this, which is here water-free oil production. So I want also to discuss what will happen at the pore scale. So we discussed the oil reservoir at a bigger scale. So what is actually happening at the pore scale? So your reservoir at the start before the migration of oil was 100% saturated with brine. Brine is the saline water, it's a salty water. So as the oil migrates from the source rock to your reservoir, it will start to invade and displace the water in front of the oil. So the oil will displace the brine. This is called the primary drainage. So in the primary drainage step, so the oil is going to displace the water, because at this case you would expect that the pressure of oil will be higher than the pressure of water. So the pressure of oil, the non-wetting phase, will be higher than the pressure of the water, and we will get positive capillary pressure, and the oil will start to push the water on front of it and occupy. So it will be pushed outside from the pores, and the oil will fill these pores. So, but the oil cannot enter these pores, else the pressure was enough to invade this pore. So how to know that the pressure is enough to invade the pore? From this expression. Okay, so the relation between capillary pressure and the radius of the pore or of the throat, you will find that there is a minimum. So the maximum, the higher the bigger the radius, what will happen? The lower the capillary pressure. So at a very small capillary pressure, if the radius of your throat was large, the oil can invade at a small. It doesn't have to. We don't have to have a higher pressure of oil. So the pressure difference between the oil and the brine, if it is very small and the radius of the throat is very big, you can invade at low capillary pressure, and this is the threshold pressure. So if you have if you know the radius of your throat, and the bigger radius of your throat, you know that you know that this bigger radius, for the oil to invade this bigger radius, this is the smallest pressure required for the oil to invade the biggest radius of throat in your reservoir. Okay, I hope that you get you understand it, and I will try to give an example on it. So, for example, I want to calculate the threshold pressure. So this is the minimum pressure required by to be exerted by the oil or the capillary pressure, the difference between oil and water, to enter the first pore in your reservoir. Okay, for the oil to start invading. So, for example, we will use this expression. So, if you know the interfacial tension, if you know the contact angle, we are talking about brine and oil, and we know the radius of the biggest radius on in your formation, so you can calculate the threshold pressure. So, for the interfacial tension of oil and water, it is a range actually from 2 to 6. So, I will take a 6 times 10 to the power of -2 Newton per meter. And if I assume that the biggest throat radius in the core plug or our formation was 10 to the power of -5, which is 1 micron. Actually, it is large. You can find larger pores than this, but this is an average. For the contact angle, we can say that our contact angle between the water, oil, and on our formation will be 72 degrees. So if you substituted all this value in this equation, you will get that the capillary pressure that we have is 3,700 Pascal, which is 0.39 psi. This is the minimum, this is the threshold pressure, which is the minimum pressure. Below this pressure, if the capillary pressure was 0.2 psi, no oil can invade in your reservoir. If the applied pressure or the capillary pressure was 0.3, no oil can enter your reservoir. So the pressure for the oil to enter, we can find the first drop of oil at a capillary pressure of 0.39, which is the threshold pressure. So according to our primary drainage, so we understand now there is a minimum pressure that the oil has to exert. So according to our so the primary drainage, or for this expression, so it is expected for the oil to fill the larger pores first, because at a very low pressure you can fill the larger pore. So what will happen for the non-wetting phase? From one pore to the other, and pushing a brine in front of it, as long as this pressure is enough to overcome the threshold pressure of your pore. Okay, so at this small pressure, if the radius is large, the oil can invade. If here the pressure, the radius is or the radius of the throat is large, the oil can invade until it forces a very small throat, which need a higher capillary pressure to apply. It will stop. It will not advance. So the oil will advance from one pore to the other pore, and still advancing as long as this pressure is enough to invade this pore. Okay, and this is called the invasion percolation. Okay, so what about if we want to fill more pores, like squeeze the oil inside? What we have to do is to increase our capillary pressure. So if you increase the capillary pressure, it will be enough to overcome the threshold pressure for this throat, and it will advance. Okay, and for example, this throat is larger than this throat, so so it can advance at a smaller pressure here. So it cannot. For example, if this pressure equivalent were for example 200 psi, and for this was 100 psi. So if you applied 100 psi, the oil will advance through this throat, and it will not be able to advance through this throat. Okay, and will not be able to push the water out of this throat. So for the you have to increase the capillary pressure to 200 psi for the oil to be able to invade this pore and fill this pore. Okay. So for the pore network, it is filled in the order of size. So this is actually, so again, if you have, for example, if the oil here was able to, so it was have enough pressure to enter this throat, the oil will fill all these pores, but will not advance here unless the pressure was enough to advance. So if it required a higher pressure, you have to apply more pressure. The oil will stop here and will not advance to the next pore until the pressure is enough to invade this throat. Okay, and go on. So it will advance from one pore to the other according to so the capillary pressure that we measure in in the lab or whatever you the way you're measuring, it is a relation between the capillary pressure and the water saturation. So for the capillary pressure and water saturation as percent, so, and capillary pressure, whatever the units you are using, okay. And there is two types of capillary pressure: the drainage capillary pressure and imbibition capillary pressure. I discussed the oil migration from the origin, so the source rock to the reservoir. It is a primary drainage. Okay, so this is what you will find here. So this is a primary drainage. As long as you increase, so as you increase the capillary pressure here, more oil are forced out of the pores. So you will get lower saturation of oil, lower saturation of oil. I'm sorry, of water, lower saturation of water, lower saturation of water, until so there is a higher step increase in the pressure until you will find whatever the pressure you are increasing, no change in the water saturation. So there is two expressions here. I want to show you in this curve. So what is the threshold pressure? I told you before, this is the minimum pressure for the oil to start to invading. So as you increase in your experiment, as you increase the capillary pressure, you will not find any oil or any change in the water saturation until you reach the threshold pressure. So the threshold pressure in this curve, you can find it here. So this is the value of the threshold pressure or the displacement pressure. So this is the value. At this value, it is the oil-water contact. You can find this at this value of displacement pressure or threshold pressure. You will find in your reservoir the oil-water contact. So what else we want to define here? It is the connate water saturation, which is the minimum amount of water that you can find in your reservoir. You cannot go lower than this. This is a characteristic of your reservoir. You cannot find a lower amount of whatever the pressure you are applying on oil, whatever the capillary pressure the capillary pressure difference or the pressure difference you are applying between the pressure of oil and pressure of water. You cannot get this water to go outside of the pore. You cannot force this oil. So at this point, we call this connate water saturation or irreducible water saturation. At this saturation, so 1 minus irreducible water saturation or 1 minus connate water saturation equal to the initial oil in place. Okay, so the initial oil saturation for this, you can find it. And the equivalent pressure, so the equivalent pressure at where you can find the connate water saturation or the end of your transition zone, you will find it from here. So at the pressure where no more, it is the first connate water formation of connate water saturation. So this is connate water saturation. You will find your pressure, equivalent pressure here. Okay. Hope that you are catching up with me. So so how this capillary pressure apply to our reservoir here? So the free water level is here, is the x-axis here, okay? And then you will start to find 100% saturation. Oil-water contact will be at the threshold pressure, okay? I showed you before, so this is the threshold pressure. So this is the threshold pressure. So you can find it, you get the value of this capillary pressure, and using the relation between height and the capillary pressure, you can transfer this capillary pressure to height. Okay, so again for the connate water saturation, so you will be able to determine your end zone at the connate water saturation, the end of the transition zone. Okay, and after this will be oil base zone, and you can find the saturation of the oil base zone or the initial water oil saturation for you from this connate water saturation. Okay. So what else happening during your production? Sometimes you do water flooding, and in this case, it is imbibition. It's called the imbibition. We know that the reservoir and the origin was 100% saturated with brine, and then the oil started to displace this brine in the primary drainage step. So the oil displacing the brine in the primary drainage during the migration of oil. So and this you will get at the end of this primary drainage, you will get the initial oil saturation. After this, you will decide to produce from your reservoir, and you do water flooding, and there will be imbibition, where the brine is pushing the oil out. So you cannot get 100% reduction in the oil, or even you can leave like 60% of the original oil in place without any production. And what will happen here is the oil will be residually trapped in your pores in the rock, and the brine will be the dominant fluid, and all the oil will be just a very unconnected distributed inside your reservoir. So this is the imbibition, and you can express it also if you force. Now you will this is spontaneous imbibition. You don't have to apply higher pressure for water. So starting from the connate water, there will be spontaneous imbibition of brine. So, and then you will force the brine inside your reservoir until you reach like whatever the pressure you are increasing, you will not get any oil out of your pores, and this is the residual oil saturation. Okay, so this is the initial oil one minus the water saturation. It will be the initial water saturation, and this will be at the end of the imbibition will be the residual saturation. Okay, so this is the residual oil saturation. So 1 minus the saturation of oil because of water here. Okay, so this is because this is the saturation of water. So a characteristic of the capillary pressure curve, we have 3 characteristics of the capillary pressure curve, which is the capillary pressure hysteresis, pore size distribution, and capillary pressure permeability. I will talk briefly on this. So as you can find here for this capillary pressure, the drainage have a curve, and this is the curve for imbibition. So how come they are not the same curve? They are not following the same path. Why? So why you would expect that for the same saturation of water, okay, at the same saturation of water, you will find the drainage capillary pressure is higher than the imbibition capillary pressure. So why? This is actually because of the contact angle hysteresis. So if you remember from part 1 in the contact angle, I talked about the receding contact angle and the advanced contact angle. So the receding contact angle is mainly the drainage. Okay, so where the oil is forcing the water, so it is the primary drainage. So this expresses the receding contact angle. So it is a smaller contact angle compared to the contact angle during imbibition, where the water is pushing the oil outside. Okay, so due to this difference, and if you remember, this is the capillary pressure equation. Okay, and if you have the interfacial tension between water and oil, it will not change. The contact angle between water and oil and the surface, your surface, it will not change. But the radius will not change, but the contact angle is changing according to the state of the displacement. If it is primary drainage, then so in this case, the contact angle will be the receding one, so it will be smaller. So the cosine will cosine the angle. If the angle is small, the cosine will be larger. So the capillary pressure will be larger. If it is imbibition, so we will substitute here with the advanced contact angle, which is larger contact angle, so the capillary pressure will be lower. Okay, so this difference, or the capillary pressure hysteresis, is due to the difference in the contact angle during the primary drainage or during the imbibition. So I want you to catch the expression. What is the primary drainage? What is the imbibition? Also, what is meant by invasion percolation, the threshold pressure. So this is some definition I want you to understand, and this will show you the importance of the capillary pressure curve. So the pore size distribution. So how come we give an indication from the capillary pressure about the pores? If you remember here, again, this equation for capillary pressure, so we have the relation between the capillary pressure and the radius. Okay, so the higher the radius, what will happen to the capillary pressure? The lower the capillary pressure. Okay, so imagine that your core, that you have a small core, and all the core have the same radius. All the cores are the same throat. Okay, all the maybe 1 micron. All the core are 1 micron throat. What will happen? We say that there is a threshold pressure. So at 1 micron, the threshold pressure that we calculated before was 0.39 psi. Okay, so if we apply this capillary pressure, 0.39 psi, what will happen to the oil? The oil will invade all the pores. Okay, so what will happen is we will go from 1 to connate water saturation at 1 capillary pressure. Okay, at 1 capillary pressure measurement. So what will happen to your curve? Your curve will be horizontal. Okay, so the horizontal, the curve, this means that the pores are the same, are nearly the same size. So there is no wide distribution of pore, no variation in your pore size. So the more horizontal your curve, the narrower the pore size distribution. But the stepper size here means that you have to increase. Okay, so if so you at your threshold pressure, you will fill the 1 micron radius. Okay, but now you filled all the 1 micron radius pores. What will happen? The advancing of oil will stop. Okay, because it invaded all the 1 micron size radius. So there is smaller. So maybe there is a half micron. So it needs more capillary pressure to invade, and then you have to apply to increase your capillary pressure. As you increase the capillary pressure, it will fill all the sizes. But there is other size. It's a small distribution. So a small portion of your oil is invading the different sizes. So this is different sizes causing us to have a stable distribution of capillary pressure, which means there is a border pore size distribution. Okay. So what about permeability? Actually, the permeability cause if you have the same type of core, but with different permeability, with different starting like from the higher permeability was K1 and the lower permeability was K5, you will find that if you have the same rock type, but with different permeability. Okay, you will find that the same shape of your capillary pressure curve, but it is shifting to the top. So as the permeability decrease, you will find a shift in your curve to upward and to the right. Okay, so you can get an indication. So the capillary pressure can give you an indication of the pore size distribution, an indication of the permeability. One of the important measurement also is the Leverett J-function, and you can directly measure it from the capillary pressure here. So this is the equation for the Leverett J-function. The nice thing about the Leverett J-function is you can compare if you have one formation and you get your core sample from different location in your formation. Okay, you would expect that every core have a different property, have a different permeability, have a different porosity. So you cannot have different pore size distribution. So you cannot compare your capillary pressure curve from this different location or for different rocks, but it is the same formation. So what you can do, so Leverett J-function has accumulated all these variables of permeability, porosity, all the state change in one curve. So you can use this curve to compare your capillary pressure or your saturation. So here you will find here. So this is showing a curve. So Leverett J-function on the y-axis and the water saturation on the x-axis. And this is a mercury injection, and this is different for different rock samples or capillary pressure curve for different rock samples from the North Sea of the same formation, and you will find it is taking the same trend. So you can compare. So you can now compare different rock from the same formation on the same curve. You cannot do this for the capillary pressure. You will not get an indication of what is happening. So the Leverett J-function is a way you can express, you can compare or have the same result because they are following the same trend. So again, before starting talking about the experimental work, I want to point out what is the importance of your capillary pressure curve. So through your capillary pressure curve, you can know the vertical distribution of your fluid or in your reservoir. You can also express this in height. So you can know the whatever the height of the free water, the oil water contact You can identify the height of the location of the oil-water contact through using this equation, the relation between height and the capillary pressure. Okay. Also, you can estimate the thickness of the transition zone, which is between the threshold pressure and the pressure corresponding to the connate water saturation. Okay, and you can express it in height. Also, you can know the irreducible water saturation, and from this irreducible water saturation, you can know the amount of or the initial oil saturation that you have in your reservoir before any production. And finally, you can get accurate measurement of your pore size distribution, and I will show this in more detail using a mercury injection capillary pressure, okay, experiment. So for the experimental work, we have actually two types of experiments that I will discuss here. So the porous plate, we will show the primary drainage using the porous plate. So there is two types of porous plate, the patch porous plate and the individual core holder porous plate. And the other experiment is the mercury injection capillary pressure, and I will show this in a separate section. So in this experimental work, I will show you how the porous plate experiments are conducted. So let's start with the patch porous plate first, but I want you to know what is meant by the porous plate. So in general, porous plate is a disc. I will show you in the video. So it is a disc, it is strongly water wet. So it will allow only water to invade it. It will not let any air or any oil as a non-wetting phase to invade it or to break through it. Okay. There is different rating for this porous plate according to the displacement pressure that you want to reach. It can be 15, it can be 10, it can be 5 bar. Okay. What I am going to show you in the video is the 15 bar. This is what I have. So the higher the displacement pressure rating, the lower the permeability of the water through this porous plate. So it will take very long time for this water to, because you want to, it is 15 bars, so the radius is very, very tight pores. So it is harder for the water to pass through, but the water pass through fine, but it takes time. So for the patch porous plate here, it is conducted at ambient condition, and it is only used for air as a non-wetting phase and the brine as a wetting phase. Okay, so this is the shape is like a container here with a cover. Okay, and you built a different core plugs. You can use regular or irregular core plugs because it depending on the weight. You cannot. It doesn't depend on the amount of water collected. So you can measure the advantage about this. The advantage about this step is that you can use several samples together. You like you can put 8 core plugs inside this patch porous plate without at the same time. Okay. And also, it is as I told you, it is air brine experiment only, and it is not recommended because you are just depending on weighting your sample, and if some of the grain in your sample that was removed, and you will get an error in your weight measurement, and accordingly the water saturation. So this is the internal of this container. So the internal of this porous patch porous plate. So this is the internal. Okay. So the air is injected here. So your core plug is placed here on top of the porous plate. So this is the porous plate and your core plug. So this is only showing one porous core plug, but you can have up to 8 core plugs. So and also you have to place filter paper here to make sure that the water, there is no loss in the water contact. So the water is advancing from this core to the porous plate in a continuous manner. Okay. So you place air, you inject air at a known pressure, at a very low pressure, and the air will displace the brine out through the porous plate, and you will find that the brine is coming out here. But you don't measure this volume. You just in an indication that you reached the end of this, at this certain capillary pressure, all the pores are invaded with air. Okay. But first, you have to weight your sample. Before starting this experiment, you have to saturate first your sample, weight it while the sample is dry, saturate it, place it in a beaker full of brine, saturate it, and then take it out of the beaker, weight it in on the balance, and then place it in here. Okay? And then you will apply the pressure here at a certain capillary pressure. Let's see, so at a certain capillary pressure here, and the water will be displaced. So what you will see here, so point by point, you increase the pressure, and then you will find some of the brine coming out until no more brine is coming out. You will open your setup, take your sample, weight it. So what will happen here, because you applied certain capillary pressure, at this capillary pressure, the air displaced the brine, there was primary drainage, so the air displaced the brine, and the brine is collected from the top here, from the bottom here, until no more brine is displaced. You reach the end point for this capillary pressure. Okay, so you want to know how the volume of brine that was displaced from your core. So you will take out your core, weight it in your on the balance. I showed every step, like the weighting and the saturation, or in the part 1 lecture. So and this will be 1 point. So you will calculate because due to the difference in the weight before the 100% saturation and after the first capillary pressure, there will be a weight difference. This weight difference, if you have the density of the brine, so you can calculate the volume of this brine, and you can get the saturation, the volume of your brine divided by the pore volume, you will get the water saturation. Okay, so you get the water saturation here, and then another point here and another point. You increase the pressure in steps until you reach the pressure where no more brine is displaced from your cores here. Okay, and then this is the end of the experiment. So you will draw this curve, the capillary pressure curve, versus the wetting phase saturation, which is in our case the brine. You cannot do this for individual core. You cannot know the amount of brine for individual core because you are using 8 or many core plugs, so you don't know which what is the amount of brine coming out from which core. Okay. And after the end, you have to clean your core using density. I'm sorry, not clean. You have to, once you reach the irreducible saturation and you weighted your sample, you get an indication of what is the irreducible water saturation. If you want to double check what you have, what is the amount of water, we can use density, where you can know the amount of water remaining in your core and compare it with what you get here. So it is just this point can be compared with using density, and after this you can saturate. Clean your core using Soxlet and dry it using an oven, a vacuum oven. The next, the second porous plate method is the individual porous plate core holder. You remember for the past, for the batch process, you will at each step you open your system, take the core out, weight it, and place it again, and close the system again, pressurize this again, depressurize, take the core out, weight it, and return it back. So it is somehow time consuming. Also, you cannot use oil; you're just using brine. There is other method which is called individual porous plate. You are using a core holder, your core holder. I showed you before the core holder, and I am going to show you how I connected or set up my core holder in the lab. Okay, in the next couple of slides. So in your core holder, this is a regular core plug, and this is the porous plate, and this is the end plug. And all this, everything are put in the core holder here, and there is a confining pressure, no contact between the confining pressure and what is the fluid inside this core plug. Okay, so the interesting thing about this is you will use only one sample at a time. One sample, you cannot use several samples, just one sample, but you don't have to take out this sample at every stage. So just you can draw your capillary pressure at one go without any disassembling of the setup, because it is hard really. This test, the interesting thing that you can use oil or air as a non-wetting phase, or whatever non-wetting phase you want to test. and the wetting phase is your brine or whatever other wetting phase you want to test. Also, you can conduct it at reservoir condition and at high pressure and high temperature, whatever you want, but it is time consuming because it takes a long time. The drainage actually take very long time. So let's start the video. Hopefully I will do this. So I want you, what you are seeing here in the video is the component of is different component for the core, the Hassler type core holder. As you can see here, this is the core plug. As I told you, it is 1.5 inch in diameter, and the length of this core plug is 3 inches. This is a standard type core holder, I'm sorry, core plug. Okay, and what is displayed here in is the porous plate. Okay, so this porous plate, I'm sorry. Okay. So this porous plate, I know this type has a hole inside, this hole through it, drill through it, but in general, the usual type of porous plate is not, it doesn't have any hole drilled through it. This is a custom made porous plate, and I will not go through why we drilled a hole through it. I will discuss it in a very rapid notes during the other experiment. So so it is the same size as the core, the same diameter as your core plug, and it is rated 15 bar. So you can see here it is written 15 bar ceramic disc. It just allow only the brine to pass through it, and no oil or air can pass through this. Cannot break through it. Okay. So in general, this is placed like this in your core holder, and if you inject brine, so the brine will be injected through here and pass through the porous plate. If you are injecting oil, the oil will just displace the brine. Only the brine is coming out of this porous plate, and no oil will be able to come. So the edge for your oil, sorry. So the edge, the last part, the further part for the oil to travel is up to this end. It cannot go through the porous plate. Okay. So we know also one of the important component for the Hassler type core holder is this end plug. So it has grooves through it to ensure that there is nice distribution of your fluid while you are injecting. So it is placed like this, and the line are used for injection of the brine or for the oil, and these grooves will make sure that there is nice distribution in your core plug, and nothing is uninvaded with brine or not saturated with brine or oil. Okay, and there is two end plug, one of this end plug, and there is other end plug, and everything are put inside the Viton sleeve, as I will show you. So it contains two holes here. This hole for the injection of different fluid. If you want one of the board to measure the pressure, or one of the board to collect one for CO2, one for the gas, whatever, one for brine, one for oil. So whatever the connection of setup that you are using here, this is our core, the body of your core holder. It is a hollow cylinder, okay, where everything are placed through here, and this you can find here a small hole. I'm sorry. So this port is for the injection of the capillary, for the injection of confining pressure fluid, okay? And there is other hole here for the injection of the capillary pressure for the air. I will discuss this in more detail in the next video. So your core here is, you will wrap your core with BTFE and aluminum foil, and then you will place it in this Viton sleeve. So this is make sure that there is no contact between the confining pressure and the fluid inside your core. And you will place your porous plate, and then the end plug here. Okay, and then the other end plug. Yeah, just I'm like demonstrating with one hand and video taping with the other hand, so you have to just bear with me for this video. So everything now is will go through this body. Okay, this cylinder. Okay, we place it inside, and then you will screw this cap here through this. This will make sure there is a pressure on both sides of your core. Sometimes you have to tilt it to just squeeze it and screw it. So this will make sure again that there is a pressure according the vertical pressure. And this is also a cap. You have to screw it here. This will make sure that also there is a pressure in your on the end plug. It is hand tight. Everything is hand tight. You don't have to squeeze it. And this is the thing I like about this Hassler type core holder. It is from Core Lab. There is different type of core holders. I was having one like it is nightmare. So this is other cap, and you have also screw it through all the way, and it is hand tight. Everything now is set up, and your core holder is ready for your flooding experiment. So so this is for the air. Once you inject this, you will use this port for to connect it with the high pressure injection pump. So I will show you here. This is the pump. So this is actually a nice pump to operate at constant pressure and constant flow. So and I have an accumulator inside. It's a very expensive pump. And there is I'm sorry. So the injected flow fills the annular space around the core, the vital sleeve, and because there is air occupying this place, so you have to get rid of this air. You don't want this will have can make some error in your pressure measurements. So you will take just place your core holder here and then get rid of the air using this valve once all the air are coming out, and you just getting water, because I would prefer to use water, okay, for as a confining pressure fluid, because oil will have it's messy, okay. But if you need to use oil, so just go on and use it, but it is really messy. What you are you are seeing here is the accumulator. Okay, so this is the accumulator, and it is connected to the high pressure pump. This is one type of pump. This is a constant flow, slightly cheaper than the other ESCO pump. And you will fill the brine through this plastic tubing and through this piston. This is a dual piston. Make sure it is continuous fluid, and the high pressure brine. I'm sorry, water is injected through this accumulator. Okay. For this, you have to take care of your piston. You don't want to ruin it. So it is important to use the accumulator. It's better to use the accumulator because and you just use just deionized water for your injection. And your accumulator have a floating piston inside. One place will be deionized water. The other will be brine or oil or gas, and then you will inject using the pump to inject your other fluid in the core holder, and they are not on contact. So the deionized water is not contacting with the oil or not contacting with the gas or whatever. And it is actually also nice accumulator from DCI. So this is a connection, and you can also connect your the different colors gas cylinders, and you can use different valves. You have to build your setup, and if you want gas or if you want oil, whatever the fluid that you want to inject to your core, you have to use your accumulator. Okay. So so we reached to the end of the videos. Now we will go back to our slides. So now you should get a nice understanding of the core holder and what is going on. Actually, the core holder or Hassler type core holder is very important. You can use in many experiments in the oil and gas, like measuring the saturation, measuring. Sometimes it is used for measuring porosity as well. You can use it for measure capillary pressure experiment, for enhanced oil recovery experiment, for the permeability, gas and liquid permeability. So it is resistivity, so CO2 storage. So it is different. It's used in different type of experiment. I'm not sure if. Okay. So what happened here? So you will inject your oil. For example, if it's a primary drainage, you inject your oil, and you are only getting brine out of this place. No oil can go through this porous plate. So only brine are getting out, and you can measure it using graduated cylinder or constant pressure receiving pump, depending on the technique that you are using. But if you are going to use a graduated cylinder for measurement, you have to use a back pressure regulator, and it is shown in the video. I didn't focus on it, but it is shown with the green knock on the Hassler type core holder setup. It was inside the back pressure regulator with a green knock. So in steps, we will go through step by step how we can conduct this experiment to measure primary drainage curve. So you have to prepare your core. This is your core, and you have to wrap it with PTFE and then aluminium and place it in a Viton sleeve. And this is another type of Hassler type core holder. This type was not the other type I'm showing in the video is nicer, is easy to handle. So the second step is to saturate everything with brine. You know, for the capillary pressure, you are mimicking what is going on in your reservoir. So first, your reservoir was saturated 100% with brine. So what you want to do this. So for your core plug, you have to saturate it with 5 pore volume of brine. So you are injecting 5 pore volume of brine. Then you will start the primary drainage step, where you just the oil is injected, and the oil displays the brine out of this porous plate. Okay, and this is the setup. So here, this is your core holder connected to injection pump, and this is a receiving pump. Instead of this receiving pump, you can install here a back pressure regulator and a graduated cylinder, but you have to account for the compressibility. And this is the confining pressure pump. Okay, so it is separated here. So for this, during this stage, so the oil is injected at a step-by-step increase in the capillary pressure. So we will start with a very small capillary pressure. For example, if you can start with 0.5 psi difference, you go on and start. If you can go lower, just to go lower. So you can adjust it according to the delta P, and both pumps are running in a constant pressure mode. Okay. So what will happen here is the oil is injected. So it is allowed to inject it, and it is displacing all the brine out of the core at this certain capillary pressure, from invading only the pores that allow that this capillary pressure will allow the oil to invade. Okay, and you only receive only brine from this core, and you can from the pore plug, and now you can monitor the volume. So you know the volume oil displays only the water. Okay. So if you have like 1 milli of oil, you will receive entering the core, you will receive 1 milli of brine. So the brine that you are receiving here is representative of the amount or the volume of oil that enters inside your core plug. So what we do here is we are going to monitor the volume received in this pump versus time. Okay, if you are using graduated cylinder, so you have to do this yourself. If this pump is connected, so its pump can be connected data logged to your computer, so you can monitor the change in volume with time in this pump just using computer. So what you find here is that as I saw, the oil is invading the pores one by one until you reach that all the pores at this certain size equivalent to this capillary pressure are invaded. Okay, and you will reach a plateau here. I'm not sure you can see. So, and you are reaching a plateau here where no more prime is coming out. So this means that at this certain capillary pressure, you reached equilibrium. Okay, so you have to monitor the amount of prime. So the amount of prime or the water saturation, because this is only one point on your curve. I want to just so. So what you have done here is only one point. So it is the capillary pressure versus one saturation of water. Okay. So how to calculate this water saturation? It is the pore volume of your core. Take away the volume of prime received in this pump. So what will happen here is the volume of prime received in this pump is equivalent to the volume of oil. Okay. So what you are getting here is the volume of water inside your core divided by the pore volume. So you now can get measure the saturation, the water saturation. And then for the oil saturation, if you can just take one, the initial water saturation, you can it is maybe 1 minus water saturation, or you can just the volume of water here divided by the pore volume. Okay. So this capillary pressure curve is nice. You can see you can there are many type like core type like Doddington, Keaton, Indiana. Everyone have a different color. Okay, and for the Keaton one, I want you to look at the rainbow type blue symbol. This represents the Keaton. I showed you the photo of the Keaton, and it has double porosity. So you can find at a very low pressure, you get just like a very low water saturation. So this means that there is very big very big wider pores. You can see through the micro CT scanner. You can see it has a very big pore. Then followed by a small pore, because whatever the change you have in this capillary pressure, you cannot force many high amount of water to come out. Okay, so that's a very low water saturation. Oil invade all the pores of the Keaton at a very low pressure, and we will still see the mercury injection capillary pressure for this Keaton, and we will show how the pore size distributed in this Keaton. So it can take many days actually. So this is one point. You will increase your capillary pressure you'll increase your capillary pressure and you will get different saturation, because oil will invade more and more pores in this in this step. Okay. So you are showing here different received amount of prime received in the receiving pump, and you can see the time consumed. So this is a very this is a high capillary pressure, higher volume of water saturation. Okay, and it takes the smaller shorter time for. This is a slightly higher capillary pressure. This is lower capillary pressure. This is the lowest capillary pressure, and you can find that it takes like 450 hours, more than, and it's 50 hours, 500 hours to reach equilibrium. So this is only one point. So each curve is representing one point. So it is time consuming, but it's important. Okay. You can also draw the Leverett J-function, because you have the capillary pressure. Of course, the interfacial tension contact angle is known. Permeability, you can measure it for your core, and porosity, it is known, because actually you have to know it to measure the pore volume. So Leverett J-function, this is for mercury injection. And also for different type of Peruvian sandstone, I can compare a different condition on the same Leverett J-function. Okay, and it is taking the same trend. Now to mercury injection, capillary pressure, and pore size distribution. Actually, for the mercury, mercury is a hard to handle, and it's not every lab have a mercury. It is toxic. So I would I was we didn't do our mercury injection capillary pressure in our lab. So we just was using Weatherford labs to do this mercury. So the mercury injection capillary pressure and the data it is measured in Weatherford lab. So mercury injection techniques can be used to measure the capillary pressure versus saturation of the mercury. So we have a curve of capillary pressure. We also have two curves of pore throat size distribution. It is a destructive test. For all the other tests I showed, it is non-destructive because you just inject in oil, water, and you can clean your core. But for this mercury test, the mercury you cannot get rid of all the mercury in your core, and your core will be damaged. So it is a destructive test. It is a fast. It is fast. It doesn't take a long time, as the case of porous plate with the porous plate. But as I told you, mercury is toxic. So here you can find here. This is the injection pump of the mercury. So this is injection pump. Okay, and there is a transparent window here where you can monitor the volume, the injected volume of mercury, and this is becnometer where you will place your sample. There will be gas cylinder to make pressure, and there will be pressure reading here, pressure reading to know the pressure, because it is a capillary pressure. You have to know the pressure of the injected mercury because you are measuring pressure versus volume or versus saturation. Okay. So in general, mercury is the non-wetting phase, and air is the wetting phase for your core. And of course, mercury will invade the larger pore first at a very small capillary pressure. Only the larger pores will be invaded, and you have to record the pressure versus saturation. So you just inject mercury, and certain volume of you apply pressure. You monitor the volume of the mercury. You get a saturation, and you measure a point. Okay, so the capillary pressure versus the saturation of mercury. So this is what we get here. Okay, so this is a Pore sandstone. Mercury injection capillary pressure curve. So this on the y-axis, this is mercury pressure, and on the x-axis, this is the mercury saturation. And you can find as we increase the pressure, the saturation of mercury increase. Okay, because it is a non-wetting phase. What we was showing before is the water was the wetting phase, so the wetting phase is decreasing. But if we are showing the oil one, it will be increasing. Okay. So you can see this curve is slightly horizontal. So you would expect that the pore size distribution will be up to 50% of the mercury is invading approximately the same pore size. I would expect it before. I'm going to show this, and then there will be a stable rise. Okay, let's see what is. So this is actually what is happening here. So you can convert this capillary pressure to radius using this equation. So you can monitor the mercury saturation versus the pore throat distribution. You will find here 50% of the mercury saturation is invading like 10 micron. So the pores are distributed in like 10 micron. Up to 50% of the pore volume are in the range of 10 micron. Okay, and then starting from this, it is gradually filling different size of pores. We have actually three sizes of pores: macro, meso, and micro. Okay, so for the micro type, it will be like larger. Macro type, it will be larger than 1 micron. Okay. So this is for 1 micron. So in the macro type, it will be larger than 1 micron. For the meso type, it will be from 1 micron to 0.1 micron, okay, in this range. And for the micro type, it will be larger than or smaller. I'm sorry, smaller than 0.1 micron. Okay. This is the capillary pressure for keton. The interesting thing is how to read this capillary pressure curve. It's important not only to measure it, but also know how to read it. Okay. So as you can see here for the mercury capillary pressure, so this is the capillary pressure of mercury and the saturation of mercury, and you can find two horizontal places here for the capillary pressure, which means that this ketone have ketone type have two distribution of pores. One larger pores, okay, because the mercury fills the larger pore first, okay. So up to 0.4% of the mercury was invading actually the same or nearly the same size of pores. So you will find here the 0.4% of the mercury saturation here is occupying like 10 micron, 10 micron pore size and smaller and larger. Okay. Then there will be start to invade one by one pores. There is some distribution of the pores here, and again, starting from 0.6 up to the end, 40% are the same size, ranging the same size, micro. Right? Here, so starting 0.65, saturation of mercury is occupying the same pore size. This is a horizontal line. Okay. And the other curve here is the imbibition. Yeah, so it is not complete, but it is imbibition. So this is and the imbibition for the mercury is just you desaturate the pore from the mercury from your system. Okay. There is another type of pore size distribution where you will find here using this relation, which is the incremental increase in saturation. So this is the saturation, this is the incremental increase in saturation, and this is a log radius, and your radius is calculated from the capillary pressure, and this is the difference. Okay. So this can be drawn in on the y-axis and this and versus the pore throat radius, and you will find that for Pore sandstone and this for ketone carbonate, for the ketone there is two distributions here. Pore distribution, one larger than 10, which is the maximum, the higher amount of pore size distribution was in the range of 10 micron and higher for the ketone, and the other one is very small, or but a group of micro porosity for this ketone, and it is smaller than 0.1 in the micro range. And if you remember the photos that I showed in the part 1 lecture, you can see through the micro CT scanner larger pore, and inside the grain itself of the ketone, it is around the grain, there is a small micro porosity. For the Pore, it is nicely distributed around 10 macro, and it is for the Pore sandstone, it is a standard pinch type and the standard type rock. Now for the enhanced oil recovery part. Okay. So what's meant by what is enhanced oil recovery? So it is a technology you can use different fluids, like you can use heat in the case of steam. You can use different fluids like CO2, nitrogen, or you can use chemicals such as polymer, surfactant, or polymer surfactant. What else? Alkaline also. You can be used for enhanced oil recovery to recover more oil. Okay, you just use normal recovery method and like water flooding, and then you reach residual saturation, and you want to increase the amount of oil that is produced, or reduce the amount of oil in your reservoir. So in general, there is different stages of your reservoir. The first thing is the 100% saturation, which was originally before the migration of oil. Then the stage of the primary drainage, where you reach initial water saturation at connate water saturation, the maximum pressure, capillary pressure, where the oil invading or migrating from the source rock to your reservoir, and then it is displacing brine in front of it. So it is a primary drainage. So in the primary drainage, it is the non-wetting phase, oil displacing the brine, the wetting phase. The third stage that we have is the secondary imbibition. If you are applying water flooding or noble production, you will find that you just produce oil, but there is remaining amount of oil inside your pores, and it can be disconnected and widely distributed around your reservoir. And through this secondary imbibition, you will reach residual oil saturation. Okay. And for the enhanced oil recovery, again, you are using another technique to reduce the amount of oil that is in your reservoir. So you will reach lower than the residual saturation here. So if this is residual saturation 1, you will reach a lower residual saturation 2. This is actually what we are conducting in our lab. Okay, so this is a different process, and you have to follow all this step in your enhanced oil recovery experiment in the lab. But before starting the experiment, I want you to understand some concept. For the gas injection, actually you have to use high pressure, inject in on high pressure formation at deep pressure, because you want to reach the miscibility pressure. You want the CO2 to be miscible with brine, because with oil, so it will facilitate the production of oil. Also, on the reverse, steam has to, but the gas injection also, you cannot use it for heavy oil, because it will create asphaltene deposition. Okay? For the steam injection, it can be used for heavy oil, extremely heavy oil, but it has to be shallow reservoir, because you don't, if it is a high, deeper reservoir, you will lose heat. Okay, so you want to be it to be economic. For the chemical injection, you can use polymer, surfactant, or whatever, low salinity water, whatever the chemical you are going to use. But for the polymer, you have to take care that it, although some of the polymer are being developed to handle high salinity water, but still the water cannot be too saline, because it will damage the property of your polymer. For the low salinity injection, of course, your saline water have to be of high salinity on the reverse. Actually, enhanced oil recovery technique are being used around the world. Two techniques actually are being applied. The most important one and the most widely used is the thermal. Okay, so it's a steam injection, and the following one is gas injection with the CO2. The other types of enhanced oil recovery techniques was not used in a wider scale. The polymer injection, the nanoparticle injection, the alkaline, whatever the process, it is if it was applied in the river, it is a very on a small scale. But the actual production, so for enhanced oil recovery, you can say that 2% of the global oil production was from enhanced oil recovery, which is corresponding to 1.7 million barrels of oil per day. Actually, there is some countries that are using enhanced oil recovery, or applying enhanced oil recovery technique, like USA, Venezuela, Canada, as you can see in this on this bar. So, how to assess that your enhanced oil recovery technique is valuable? So you have to measure the recovery factor, which is the amount, the initial oil in place. No, I'm sorry, the ratio of oil production. So the oil produced divided by the initial oil in place. Okay, so you can say this is the residual oil saturation, and this is the initial oil saturation. So you can say this. Actually, the recovery factor may be expressed on a different, as an efficiency, the displacement efficiency, and the sweep efficiency, the connected volume factor efficiency, the economic efficiency, and the red one here, the red efficiency, can be increased using enhanced oil recovery technique, like the displacement efficiency and the sweep efficiency. The displacement efficiency can be increased using the capillary number, or alternating the capillary number, and for the sweep efficiency can be used by alternating the mobility ratio. And we will see now in the next couple of slides, I will discuss this. So there is three concepts that you have to know once you are designing your enhanced oil recovery technique, and this will impact the amount of oil that you are going to recover using this technique. The first one is the capillary number, the second is the gravitational segregation, and the third is the mobility ratio. So this is three concepts you have to understand, and you have to design your technique around it. So for the capillary number, it is actually the balance between the viscous force and the capillary force. And this is the equation that you are using capillary number. So this is the viscosity of the displacing fluid, which is in this case the prime, okay, and the velocity, and for the interfacial tension, okay. So what you have, so if in the case of that the capillary forces was dominant, okay, what will happen that you find that the capillary number will be higher than, I'm sorry, smaller than 10 to the power of minus 5, okay. So the lower the capillary number, okay, the more dominant the capillary forces. The higher the capillary number, the dominant is the viscous forces. So what can this do any favor for enhanced oil recovery? Can we benefit from these expressions in enhanced oil recovery? Actually, yes. From this curve, you can see here for the capillary number on the x-axis and the oil saturation from starting from 0 to 1. Okay, so this is the direction of increasing of oil oil residual saturation in your reservoir. So in this direction, the amount of oil in your reservoir increase. And this direction, the capillary number, in this direction, the capillary number decrease. Okay, according to this curve, as you decrease the capillary number, the amount of residual oil in your reservoir increase. Okay, so the more, the lower your capillary number, the more the residual saturation of your oil in your reservoir. Actually, it doesn't, up to 10 to the power of minus 5, it doesn't affect the amount of residual oil. So do you have to increase, do you want in enhanced oil recovery to increase our residual oil saturation, or we want to decrease it? We want to decrease it. For the enhanced oil recovery, we want to decrease the residual amount of oil in place. So what we will do, we will increase the capillary number. We want this capillary number value to increase up 10 to the power of minus 5 or 10 to the power of minus 3. So the lower the capillary number that you can, the higher the capillary number that you can get, the more oil that you can recover. So how can we change this value of capillary number? You can increase, we want it to increase. You can increase the viscosity of the displacing fluid. So if you used polymer, you will increase the viscosity, okay? You can increase the injection velocity. You can decrease the interfacial tension, like the miscible fluid or using of the surfactant. Okay, so this is using miscible fluid, using surfactant will decrease the interfacial tension. Using polymer will increase the viscosity. So this is how we can control this capillary number. And I will give you an example here. So if the velocity in your reservoir was 10 to the power of minus 5 meters per second, interfacial tension was 6 times 10 to the power of minus 2 Newton per meter, and viscosity of water 10 to the power of minus 3 Pascal second. Remember, this is an estimate number, it's not an exact number. So what you will find here in an actual oil reservoir, what is happening? The capillary number is 10 to the power of minus 7. What you want here is to increase this by 100. So to reach 10 to the power of minus 5 to 10 to the power of minus 3. Okay, this is can be conducted by altering the viscosity of your displacing fluid. So the brine, you will inject polymer with your brine for increase the velocity, but you are limited with the velocity, and decrease the interfacial tension. So what will happen when the viscous force is the dominant force? So once you increase the capillary number, the viscous force is the dominant force. What will happen that you will get a piston-like advance. So the brine will act like a piston. It will push the oil in front of it. It will not bypass. So it will not just bypass the oil and trap the oil in the middle of your pores. So trap the oil in the middle of your pore. This will not happen if you are using a high capillary number or high flow rate. So what will happen? You want all the time, you want your water to be acting like, or your injecting fluid, you will be acting like a flat connect or a piston-like advance, not a snap off or bypass. Okay, this is an expression of where the water is just passing the oil and trapping it in the middle of the pore. This is the snap off, or snap off also, or bypass. So what is about the gravity segregation? If the difference between the density of your injecting fluid is very high, what will happen that in the case of the gas, for example, the gas will float to the top and will happen bound effect. So the gravity, so the CO2 will leave your crude oil and will float in the top, and you don't want this to happen because this will reduce the amount of oil that you want to recover, and we want to prevent it. So actually this is happening in the case of injection of the CO2, of injection of natural gas or any light gases. So what happens that the CO2 will float and will have the viscosity fingers or viscosity of gravity segregation will I'm sorry, not viscosity finger, gravity segregation or front here, tongue here, gravity tongue will occur. Okay. And this is why the water alternating gas technique are used to overcome, because the water is heavier than the gas, so it can to some extent lower the gravity segregation of the gas. The third concept here is the mobility ratio or the sweep efficiency. So the sweep efficiency in general is the relation between the relative permeability of water times the viscosity of oil divided by the relative permeability of oil times the viscosity of water. So in general, if this mobility ratio was smaller than or equal to 1, you will find that the water will be traveling as a piston-like advance. So it is pushing the liquid. It will not be of a higher velocity than or higher speed than the oil. Okay, so it will all the oil and the water will travel at the same speed. So it will act like a piston advance. So it will have higher sweep efficiency. Okay. So the lower the mobility ratio, the higher the sweep efficiency. So what about if the mobility ratio was greater than 1? What will happen? Okay. So if the mobility ratio is greater than 1, this means the water will travel at a higher speed, or the injected fluid will travel at a higher speed. If the injected fluid, so imagine in this photo, this is injected fluid, what will happen? It will travel on a higher speed, more than the oil. So viscosity fingering will occur, and you don't. This means that there will be water breakthrough, and you don't want this. This means that you will not get an oil, you will get a low sweep efficiency, and you will get low oil production. Okay, so the mobility ratio is inversely proportional with the sweep efficiency. Okay, and for example, so when we achieve if you are looking at the viscosity of the oil and viscosity of the water, we want to achieve a lower mobility ratio, which means that we want to increase the viscosity of the water. If we want to increase the viscosity of the water, we apply polymer flooding. So polymer flooding will increase the mobility, will decrease the mobility ratio, and will increase the sweep efficiency, and we will get oil production. So this is how you can design your enhanced oil recovery experiment. So the capillary number, you have to design your experiment so that the capillary number is higher than 10 to the power of minus 5 to 10 to the power of minus 3, which means high displacement efficiency, and the initial residual oil and the amount of oil that is in your reservoir will be decreased. Okay. For the gravity segregation, you have to make the pressure, the density difference between the injected fluid is not very high to avoid gravity segregation, and the mobility ratio has to be lower than or equal to 1 to have high sweep efficiency and to lower the chance of viscosity fingering. So now to the experimental work part for this core flooding. I know it is a long lecture, but I hope that you understand what I'm delivering to you. So for the core flooding experiment, you have to, there is some steps here you have to follow to prepare your core. Okay, as I saw in your lab, you are preparing first. You are saturating your core with brine. The early stage of your reservoir, then you will simulate the oil migration, which is the primary drainage. You are injecting oil, then you will simulate water flooding, which is the imbibition. Then you will inject the enhanced oil recovery fluid. Okay, So the first step is you have to prepare your core. It is for all the steps that or the experiment in petroleum industry. You have to prepare your core, wrap it with PTFT. Sometimes you don't need to wrap it with aluminum, but it is better. So aluminum, and then you place it in the vitamin sleeve, place it in the core holder. So this is the setup. So your pump, and there is 3 accumulator, 1 for oil, 1 for brine, and 1 for, what I'm showing you is an experiment for nanosilica. This is a published paper on nanosilica, and this is a confining pressure pump, and this is bag pressure regulator, and this is a graduated cylinder. So what happened here is that you will vacuum your system, make sure that it is air free, and then you start injecting 5 pore volume brine, which is you have to saturate your brine first with 100%. Make sure that your core saturate your core. I'm sorry. So saturate your core or pore volume of your core with 100% brine. Then the next step is to simulate the migration of oil in your reservoir, which in this case you have to inject oil. So the oil is injected in your on your reservoir, and the brine is displaced. Actually, you can use the porous plate here if you want to reach higher initial water saturation. So the porous plate will allow you to increase the water the residual saturation of oil. Okay, I'm sorry, the initial saturation of oil. So you can use oil. So the oil will displace the brine out of the core, and in some experiments you don't have to use the porous plate. But actually, the initial saturation of oil here that you will start with will be slightly small. But you can adjust it using the back pressure regulator and the pressure of the oil. Okay? The back pressure regulator pressure of the oil can control your pressure inside your core. So, okay, so what will happen here is the oil will displace the brine outside of your core, and until no more, so you will keep injecting oil until no more brine is coming out of your is received. You don't have to receive more brine, so you constant oil and constant no more brine are coming out of your core. So you assume that you reached irreducible water saturation. So you will you calculate the irreducible water saturation, which is the volume of brine that you collected, you get out of the core, divided by the pore volume, and this all value is subtracted from 1. So now you get the irreducible water saturation in your core. Again, the initial water saturation can be one takeaway is irreducible water saturation. Okay, so this is the second step. So it is the primary drainage step. All the step we are preparing our core for the enhanced oil recovery step. The third step is the secondary imbibition, which is in this case is the water flooding. So what we do here is to inject brine again in this core, and the brine, what will happen? The brine will displace some of the oil out of your core, and some of the oil will be remaining inside, residually trapped in your core. So what you want here is to calculate the residual oil saturation, and you can calculate also the recovery factor, which is the amount of oil produced divided by the initial oil in place. So the amount of oil produced here, so you will continue until no more oil is produced. Okay, so this is step. So the brine will displace the oil out of the core, and you will continue running this until no more oil is displaced. So what we have here is the brine is injected. Okay, and the recovery factor is calculated. It is dependent on the oil production. So what you will find here is the oil production will increase until no more. So you reach plateau. No more brine is produced. No more oil is produced. So you can calculate the residual oil saturation in your core. It is the amount of oil, the volume of oil that you received outside divided by the pore volume, take away the initial oil in place. Okay, so this is the equation that you are using to calculate the residual oil saturation. So what about the recovery factor? It is actually the volume of oil, the oil produced, the volume of oil that you received, divided by the initial oil in place. So initial oil saturation at the bottom, and the volume of oil divided by the pore volume, because you wanted to make it saturation, okay, to get a saturation. So this is the recovery factor. This is how you calculate the recovery factor. The fourth step is the tertiary recovery. So for the tertiary recovery experiment, so now you are injecting brine, okay? So we reached at this step. In this step, we will start from this point and we will use our enhanced oil recovery fluid. So in this case, it's a nanosilica, okay? So what will happen here is the oil will start, we reach it at the end of water production that no more oil is produced. But once you start to inject silica or polymer or whatever the enhanced oil recovery fluid that you are using, some production, some oil will, you will monitor some of the oil are getting out of your core and you are receiving more oil. So the silica are injected here, okay? And your oil is, you start to receive oil from out of your core, and you will continue flooding, okay? So the water flooding will continue until no more oil is received, okay? And you are reaching a plateau. So what is happening here, as you can see here, if you nanopolymer will just displace some of the oil out, the residual oil out, and it goes with the nano particle brine, and the oil is coming out. This will continue until no more oil is coming. And you will calculate the residual saturation at the end, which is the volume of oil collected at this step divided by the pore volume of your core, and you will take away this value from the residual oil saturation at the previous stage, step 3. Recovery factor, again, it is the oil production divided by the initial oil in place. Recovery factor here is cumulative, okay? So it is the volume collected in step 3 plus the volume of oil collected in step 4 divided by the pore volume, all of this divided by the initial oil in place, which is the initial oil saturation, which is calculated in step 2, which is the primary drainage, okay? You can calculate also displacement efficiency for this type of enhanced oil recovery nanosilica. So it's the residual saturation after applying the nanosilica divided by the residual saturation when we applied residual oil saturation, when we applied just water flooding or brine flooding. And this will be take away from 1 times 100. So you will get enhanced displacement efficiency as a percent. You can in this case, we use silica nanoparticle as a tertiary recovery technique. But sometimes, so we started with brine until we reach a plateau. So then we started with the silica nanoparticle until we reach another plateau. But sometimes we want to play. So we, instead of water, if we started with water flooding, you start directly with. So this is the water flooding. We start directly with the silica nanoparticle and see if we don't have to apply secondary to be tertiary technique. We can directly inject silica instead of water flooding and see. And actually, there is interesting higher recovery when we use silica. Like a concentration of 0.1%, which is the highest recovery. So this is the end of lecture 2, and I hope that you did enjoy it. I know this it is a long lecture, but hope the best for you. Thank you.
Dr. Rehab, thank you very much for the great experience you are sharing with us, and for the audience. Please, if you have any question, please write it below the video on YouTube or in the video on Facebook, and we will collect these questions and we will send it to Dr. Rehab, and we promise to get you the answer as soon as possible. Thank you, Dr. Rehab, again.
Thank you.